Welcome to the Crazy Hat Chemist. So today we're doing another video here on atomic structure and electron configuration. So let's get moving. Bam! We're going to calculate the wavelength using the Bohr model. And we're going to calculate a specific wavelength here today. So I'm going to read the question. It says the following. We're going to calculate the wavelength of the green line of an excited hydrogen atoms using the Bohr model. That is a fall of an electron from n equals 4 to n equals 2. Remember, it's always the high minus the low. Okay, so this is the equation that we had on the previous lecture video here. Hopefully you remember that. That's a change in energy is the energy final minus the energy initial is equal to negative RHC times the quantity of 1 over n squared final minus 1 over n squared initial. We're going to plug into this here really simply. We know what RHC is equal to because we've already calculated E sub 1, and that is that value right there. And then we know the value of the final and the initial. Remember, the initial is the n equals 4, the final is the n equals 2, because it's going from high energy n of 4 to falling to n of 2. Then light is emitted according to that. Okay, so that's why we have this. That's negative 1312 kilojoules per mole times 1 over 2 squared minus 1 over 4 squared. We're going to get a number here for that, and that is equal to this. So this is the change in energy. It is negative 246.0 kilojoules per mole. Now you're going to say, well, that negative sign tells you that this is exothermic. That means that light is being emitted. So the question is, can you have a negative wavelength? The answer is no, you can't have a negative wavelength. We calculate wavelengths as positive values here for chemistry. Okay, so what we're going to do is we're going to get rid of that negative sign, knowing that it is an exothermic reaction. That is, heat is being liberated in the form of light being emitted. And that's the key here. So we're going to get rid of the negative sign because we know that light is being emitted, and that is the energy that's being released. Okay, so now we're going to convert this into another set of units here. We're going to take that energy of a photon is going to equal that 246 kilojoules per mole. That is positive. Okay, we're going to get rid of those joules, and the kilojoules and get joules, and then we're going to get rid of the moles, and we're going to have photons. So now we have joules per photon. So that's 4.085 times 10 negative 19 joules per photon. Now, what we're going to do is remember a previous equation of which we have used before here, and that is this one here. E is equal to hc divided by lambda. That is, energy is equal to Planck's constant times the speed of light divided by the wavelength. So what we are solving for on this problem is the wavelength. So what we're going to do is we're going to rearrange this equation and solve for wavelength. I'm going to do that right now, and here's what I got. So the lambda, that's wavelength, is equal to c, which is the speed of light, times Planck's constant, that's h, divided by the energy per photon. And that's going to be in joules per photon. And that's the number that we solved for right there. That's why we did the unit conversion right there. Instead of leaving it as kilojoules per mole, this allows us to cancel out the units as appropriate. Okay, so we're going to plug in the numbers. Here we've got the speed of light, that's the 2.998 times 10 to the 8 meters per second. We got Planck's constant, that's 6.626 times 10 to the negative 34 joules seconds per photon. And then we've got the energy per photon that we calculated previously here for that change in energy going from 4 to 2 of n of 4 of n of 2. And that's 4.085 times 10 negative 19 joules per photon. Okay, you should see that the photons cancels out, the joules cancels out, the seconds cancels out, and we are left with meters, which is a length, which would be a wavelength. So this is the value in meters. That's 4.863 times 10 to the negative 7 meters. Now you're going to ask yourself, well, is this a valid wavelength? It is most certainly a valid wavelength. But in the visible region, we like to use our wavelengths and convert them into a similar set of units. And those similar sets of units are in nanometers. So we need to convert this into nanometers. And there's this conversion into nanometers right there. And then we're going to get our value of the wavelength from the n equals 4 to n equals 2 calculation. And that wavelength is 486.3 nanometers. All right? Okay? So make sure that you can do this calculation. You need to repeat this calculation. It's a very vital, important calculation. This wavelength calculation is what Niels Bohr did, and this is why the Bohr model for the atom works so well for single electron systems. And he was able to calculate the wavelength of all 4 bands in the hydrogen atom spectrum. And you should be able to do the same. We got one more slide here to show us what's coming up next. We're going to look at the light production from hydrogen. And I got a super cool hat here. I don't know if you've watched any of those Harry Potter movies, but I am most certainly a wizard of chemistry, absolutely. Give me a thumbs up if you like that video. Give me a thumbs up if you like Harry Potter movies or the Harry Potter book series, because that's even better. And subscribe to my YouTube channel so that you can see more cool chemistry videos on all kinds of cool chemistry stuff. See you later. Bye now.